Alright, so let's see if we can put all this stuff together and look at the graph of this function. F of x is x minus 1 times x plus 1 over x squared. And let's just throw the whole shebang at this and see what happens. Because we're going to analyze this in a lot of different ways, I'm going to play around with this, write it in a couple different ways, because some ways might be more useful than others, just with an eye towards the future. You multiply that together with the difference of squares. And also I could rewrite this another way by dividing it through and saying that this is 1 minus 1 over x squared, right? If I have a fraction on the top, difference on the top, then the fraction breaks up like that, right? So I can write this as 1 minus 1 over x squared, or even more simply, 1 minus x to the minus 2, which is really the greatest way to write it if I wanted to, for example, take a derivative or something like that. Okay. So let's start by figuring out the shape of the graph of this function in terms of its derivative and its second derivative. So the first derivative of this function I can find by looking at the derivative, how it's written over there. So the minus 2 comes down, so I get a minus 2x to the minus 3, so I get a minus x to the minus 3. Minus 2, I get a 2x to the minus 3, right? 2x to the minus 3, which I could also think of, if I wanted to, as 2 divided by x cubed. While we're at these derivatives, why not just write down the second derivative as well? So I'll use this form, because that's the easiest to look at, and you get minus 6 x to the minus 4, or in other words, minus 6 over x to the 4th. Okay? So let's record that information at the side of the board for future reference. So the derivative is 2 over x cubed, and the second derivative is minus 6 over x to the 4th. Can we still see that? Let me slide it over a little bit. The second derivative is minus 6 over x to the 4th. Yeah, okay, still on the screen, good. Okay, so give myself a little room to work here. We can then proceed to make a sign chart, keeping track of the derivative, keeping track of the sign of the derivative. And we could also make a sign chart for the original function. How about that too? So for the original function, we would like to mark down the places where the function is either 0 or discontinuous. Conveniently, I have it written down in kind of a factored form over here, and you can see that, that the thing is equal to 0 when the numerator is 0, which gives us the points 1 and minus 1, and it's discontinuous at 0. So there are these 3 points of interest where the function could potentially change sign from positive to negative. Let's go through them. Well, if we're all the way on the right, then if I'm bigger than 1, then this is positive, and this is positive. Everything is positive in sight. The function is positive. If you fall less than 1, then after subtracting 1, you become negative. So this term is negative. But since I'm still positive, the other 2 terms are still positive. I have 1 negative, and some positives gives me a negative. To the left of 0, both terms on the top are to the left of 0, this term is still negative. But if I add 1, if I'm in between minus 1 and 0, this is going to be positive. This term is squared, so it's positive. So what do I have? I have a negative, positive, positive, I get a negative. And then to the left of minus 1, I have a negative, negative, and, well, 2 negatives make a positive. I got, either 2 or 4 negatives, depending on how you'd like to count. Upshot is it's positive over there. This is a sign chart for the function. Roughly speaking, this says I'm above the axis, below, above. Maybe I'll make these in green, the vague shapes of the graph. I'm up, down, up. How about the derivative? Well, the derivative is this function 2 over x cubed. And for this guy, I need to mark down the places where the derivative is either 0 or not defined. For a fraction to be 0, the numerator has to be 0, and 2 is never 0. That doesn't happen, but it is undefined at x equals 0. And now I should mark where the derivative is positive or negative. It's 2 over x cubed, and if you plug in something positive, it's positive, and if you cube a negative number, it's negative, negative back here. That says, in terms of the shape of the graph, that we're going up, that we're going down on the left. The derivative is negative, so we're decreasing, and then we're increasing on the right over here. So that's that basic information. As for the second derivative, well, this, again, is not defined at 0 and is never actually equal to 0. This x to the 4th is always positive because it's an even power, and this minus 6 means that you have a negative divided by positive, negative everywhere. This means we're concave down in both these zones. Putting these two pieces of information together, I find that on the right-hand side, I'm increasing in concave down. That means on the right-hand side I have this kind of a shape, to the right of 0. And to the left of 0, I'm decreasing in concave down. So that means I have to have this kind of shape on the left-hand side. Yeah, decreasing, concave down, increasing, concave down, yeah. Okay, and then also I have this sign chart of where I am above and below the axis. Okay, so let's take this information and make a rough sketch so far. I've used that information, I'll erase it. Mark a few points of interest. We have -1 and 1. I mark those points because I know the graph passes through those actual points. On the left, I'm decreasing concave down. On the right, I'm increasing concave up, so it looks something like that. And now the only question is, well, what's happening as we get close to 0, and what's happening as we go to the edges? We know that there is something to look for at 0 because of the initial function has 0 in the denominator, which means 0 is not in the domain. So this is a place that we might look to find potentially a vertical asymptote or something like that. Because asymptotes, by definition, can't be points of continuity, right? Because if you were continuous, that means the limit actually has to be the value, but if the limit is off at infinity, that can't be the value. So these are discontinuous points, and rational functions are discontinuous if their denominator is 0. This x equals 0 is a place to look for a potential vertical asymptote. So let's go ahead and look. How would we do that? We check and see what the limit is as x goes to 0 of f of x. So the limit as x goes to 0, for example from the right, of x minus 1, x plus 1 over x squared, what do we find? Well, we find that to the right of 0, well, this is close to -1, this is close to 1. So we get something like -1, 1 divided by small positive squared. And so what does that tell us? That gives us negative dividing by something small and positive gives us something big and positive. So we get, and the negative from the top, so we get minus big basically. This goes to negative infinity. Just like in the picture, what it looks like, we actually know that we now have an asymptote coming from the right to minus infinity. Similarly, we could look on the left, and actually the work looks exactly the same. So I'm just going to modify these to minus signs. And we find just again that we're now squaring a small negative instead of squaring a small positive. But you square it, it's positive anyways, you get the same answer, minus big. You get these asymptotes like that. Now finally, to complete our picture, let's look at whether or not we have horizontal asymptotes, the behaviors on the edge. So there we would look at the limit, for example, as x goes to infinity of f of x. There's a lot of different ways that we could look at this expression. I think the most easy one to look at is probably this one, right? But just for fun, let's look at this one, because then we can use L'Hopital's rule, and that's fun, right? So let's look at that one just for fun. We would get x squared minus 1 over x squared, and we can see that if we just tried to evaluate the top and bottom separately, they both get large. Big squared is big squared minus 1 is big over big, infinity over infinity. This is an indeterminate form of the type that L'Hopital's rule applies. And that tells us that we get the same answer for the limit by taking the derivatives of the top and the bottom, which in this case are both 2x. And so we end up getting 1. That tells us that on the right now, as we go further and further out, we approach 1. But we could do the same analysis as x approaches minus infinity as well. And again, what we find is that, well, negative infinity, when you square it, is just some big, and again, an infinity over infinity, you take the derivatives. Derivative of x squared minus 1 is 2x, derivative of x squared is 2x. The limit is 1 again, and on the left, we get that picture as well. And now we have some relatively complete collection of features of this graph. We understand how its concavity is. We know what the limits are as you go to the sides. We see where the vertical asymptotes are. We have a couple of points on the graph, etc. And there we go. Isn't it beautiful?